Today, I ask, why is the sky blue? It is a simple question. You probably think you know the answer. But, do you really know? Well, let's go back to time to see how great people in the history think. But first,
너 하늘이 왜 파란 줄 알아?
그야 저 햇빛이 공기 중에 난반사돼서 흩어진 거.
틀렸어. 나를 위해서야. 내가 하늘은 파랗길 원하니까 파란 거야. 알겠어? 너 불이 왜 뜨거운 줄 알아? 나를 위해서야. 내가 불은 뜨겁길 원하니까 뜨거운 거야.
Look up at the sky on a clear day. The sun is white. Space behind the atmosphere is black. And the gases surrounding Earth are almost completely transparent. So where does all that blue come from? It seems like a simple question. But for more than 2,000 years, some of history's greatest thinkers looked upward and arrived at very different answers. The sky is not a blue surface. There is no blue ceiling above us. When we look upward, we are looking through a thin layer of nearly transparent air, and beyond it, the darkness of space. Somehow, white sunlight enters that air, and blue light reaches our eyes from almost every direction. So the real question is not, what is blue up there? It is, what happens to sunlight along the way? Aristotle believed the color appeared when light interacted with darkness. Centuries later, Leonardo da Vinci connected the blue sky with illuminated air or moisture seen against the darkness beyond it. These explanations were not modern science, but they contained an important intuition: the blueness was not necessarily an object. It emerged from a relationship among sunlight, the atmosphere, and the darkness of space. But something essential was still missing. What exactly is white light? In 1666, Isaac Newton sent a beam of sunlight through a glass prism. The white beam opened into a spectrum: red, orange, yellow, green, blue, and violet. Newton showed that the prism did not create these colors. They were already present inside the sunlight. Now the sky problem became more precise. If sunlight contains every visible color, why does the atmosphere send mainly blue light toward our eyes? In the 19th century, Lord Rayleigh found the mathematical relationship at the heart of the answer. When light encounters particles or molecules much smaller than its wavelength, different colors do not scatter equally. The strength of this scattering varies approximately with 1 divided by the wavelength to the 4th power. That 4th power is crucial. A relatively small difference in wavelength produces a very large difference in scattering. Rayleigh's theory showed how wavelength controls scattering. Later work, including Einstein's treatment of molecular density fluctuations, helped connect that scattering to the microscopic behavior of matter itself. Imagine a wave of sunlight reaching a molecule of nitrogen or oxygen. The light's electric field briefly disturbs the molecule's electron cloud. That temporary separation of charge behaves like a tiny oscillating dipole. It re-radiates, or scatters a small amount of the light in other directions. Blue and violet light have shorter wavelengths than red and orange light. Because Rayleigh scattering depends on the inverse 4th power of wavelength, those shorter wavelengths scatter much more strongly. So blue light is much more likely to be redirected toward your eyes from another part of the sky. In a clean, cloud-free sky, scattering by nitrogen and oxygen molecules produces the characteristic deep blue. As aerosols become more important, the sky loses saturation. Humidity often enlarges those particles, producing a pale or milky haze. Water vapor itself is not a visible white gas. Smoke, dust, and pollution can dominate under hazy conditions, reducing visibility and shifting the sky toward gray, tan, or yellow. Cloud droplets and ice particles scatter visible wavelengths broadly, so clouds appear white when thin and gray when optically thick. Clean air gives blue its strongest voice. Larger scatterers progressively wash that blue toward white or gray. So why isn't the sky violet? The sun supplies somewhat more blue light around 450 nanometers than violet light around 400 nanometers. However, the atmosphere pushes in the opposite direction. Because violet has a shorter wavelength, air molecules scatter it about 60% more strongly than blue. These effects partly counteract each other, so the physical skylight overhead contains substantial and sometimes comparable amounts of blue and violet. But the sky is not viewed by a neutral detector. Light must pass through the optics of the eye and activate 3 types of cone cells. Human vision gives the violet end of the spectrum less perceptual weight, and our brain interprets the complete scattered mixture as a bright, slightly unsaturated blue, not as an equal mixture of blue and violet. The atmosphere determines the scattered spectrum. At the end of the day, the human visual system determines the color we experience. The same mechanism explains why sunsets are red. At midday, sunlight takes a relatively short path through the atmosphere before reaching us. Near sunset, the light enters at a shallow angle and travels through much more air. Along that longer path, much of the blue light is scattered away from the direct beam. The colors that continue toward our eyes are increasingly orange and red. The blue sky and the red sunset are not separate mysteries. They are 2 views of the same process. To wrap up, we began with a simple question: why is the sky blue? Sunlight brings every visible color. Air molecules scatter the shorter wavelengths much more strongly, redistributing blue light across the sky. Then our visual system interprets that scattered mixture as the blue we experience. From the blue dome at midday to the red horizon at sunset, the same process explains both. The sky is not a blue object. It is a planetary scale experiment in light, happening above us every day. Nature did not change. Only our understanding did. Even great minds did not get it right the first time. So, ask why. A whole world awakens.